So welcome everybody. My name is Thomas Von Johnston. I am an assistant professor at the psychology department at Durham University, and I'll be moderating today's Durham RIOTS talk. And we are absolutely thrilled to have Dr. Jill Jacobson with us here. So Jill is an associate professor at Queen's University, and she has taught statistics and research methods at the undergraduate and graduate level for the last 20 years. She studies a range of topics that often focus on the social cognitive consequences of self-related constructs, including causal uncertainty, depression, and more recently, self-esteem importance. An increasing focus in her work engages as well with meta-scientific questions, including a federally funded project that examines how participant non-naïveté can influence study results. On a more personal note, Jill was effectively my co-supervisor at Queen's for the last 7 years and has been an enormous part of my interest in the self literature, but also my growing interest in open science and replication. So I'm really just super pleased to have been given the opportunity to invite her here today. Before the talk begins, just a couple of quick kind of bookkeeping notes for the purposes of clarity. So the first thing is, due to my own mistake, some of the advertisements for this talk mistakenly overbroadened Jill's focus for the talk. Actually, the talk will specifically focus on the interpretation of replication results, not the implications for original research. So I do apologize for any confusion on that front. Second, please do ask any questions you have for Jill along the way using the Q&A section. I'll be monitoring those questions as they come up, and other people can actually see your questions, so please do upvote them if you have similar questions, and I can use that then to help sort of select questions to ask Jill if there's too many to address as we're going. But with that, I will turn it over to Jill to begin. So thank you very much, Jill.
So thank you, Thomas, for the nice introduction. And I will say to the people at Durham, Queen's loss is your gain. Thomas is a wonderful colleague and researcher, so I hope that you appreciate him and get an opportunity to work with him and get to know him. So today, I'm sorry I can't talk about that broader thing. I would find it very hard to talk about that in a general way. My goal really today is to focus on how we decide if something has replicated or not. So I am going to make some assumptions that if you are a member of a club called RIOTS, that you already know things about like the BEM and the replication crisis and the Reproducibility Project. I've been attending a lot of these talks now that everything's been remote. And I'm always surprised that people go all the way back to that when they're talking to an open science group. So I'm hoping I can skip that. But if you aren't familiar with those things, hopefully you will get to know about them, but I am going to assume that we have that kind of base level of knowledge of things. And so the reason I chose this topic is actually somewhat selfish as well. I used to get to teach an undergrad course where I could bring in these open science topics. And so I could save a lot of the information I find, and I could kind of put them together, but I'm no longer teaching that course. And so this was an opportunity for me to go and get caught up and revisit some of the different ways that we do make these assessments, because it is something my lab is doing more and more, is doing more replications. So that's sort of the background that I'm approaching this with. And so one of the things that you will find is that there is no consensus about how we should deem something to be a successful replication or not. So this is from Nozick and Arrington. This was in eLife about the Cancer Reproducibility Project. And so this was what eLife actually, one of the highlighted quotes that they took out of it. And indeed, there's no consensus about what constitutes a successful replication, but there is a lot of consensus that there's no consensus about that. So this is from Asendorf in 2013. This is from Kammerer in 2016. From Zwan in 2018, Labelle in 2019, Hedges and Schauer in 2019, Hung and Fithian in 2019, and then a more recent one, a preprint in 2021. So we seem to have good agreement that we don't really know what we should use. And I find that is something I hope the field starts thinking about more and moving towards more, because if you are going to do replication, I mean, if you go to the replication recipe to pre-register your replications, one of the things you have to say is, how are you going to decide what was a successful replication or not? And I was looking at, there was recently some materials posted on FORT, so an open science teaching resource, and on how to do a replication, but they skipped this part. They didn't include, like, how are you going to decide if it was a successful replication or not? So this is a non-exhaustive list of the things I'm going to touch on a little bit today. I am going to give every one of these probably short shrift, and I'm not, it's definitely non-exhaustive. There are definitely other ways that people are doing it. Even if you look at the most recently published many labs, they're doing 2 new things. So there seem to be developments on this all the time, which is good. But it does mean that if we look across the literature on prior replications, especially those kind of many labs, multiple study, many laboratory ones, there's not going to be a consistent one that's being used. But I'm just going to take each of these in turn, talk about what it is, and then talk about maybe some of its criticisms, and then also kind of show you how it plays out in some of the ones you might know about, like the Reproducibility Project. So the first one I'm going to do is the replication p-value. So this is my shorthand for saying that the replication study found a significant effect, right? So this is far and away the most common way that people assess replication success. It's the easiest one because we probably are going to do a statistical test, and it's easy to get that p-value and see what it looks like. But I do think in many ways it's the most problematic, and that's just not my opinion alone. But let's look at what it is. So this is actually real data. This is a study led by Thomas from my lab. And the details of the study don't matter so much, but I just want to kind of use this as an example. So what I have here, these are from the original study. The line is the confidence interval. That diamond is the point estimate for the effect. These are raw effect sizes. And so we can see that I'm going to show you then what we found in the replication. So you can see this replication confidence interval crosses 0. So, so that would be a non-significant effect, right? So we would say that's a replication failure. This one also crosses 0. So we would say that also failed to replicate. And so those both would be considered replication failures. Well, there were some other dependent variables. So you can see this one doesn't cross 0, nor does this one. And so those would both be considered replication successes. So that's what I mean when I talk about the p-value. So we can use the confidence interval here the same way. If the confidence interval contains 0, then it is going to be non-significant p-value. If the confidence interval doesn't contain 0, then it'd be a significant p-value. So other criticisms, so Maxwell and colleagues in 2015 were pointing out, often when we see what we saw there with those first 2 effects, is that we mistakenly think that therefore the effect is 0. So when we find that something is not significant, we conclude that there is indeed a null effect. So the evidence of absence does not mean the absence of evidence, or whichever way that goes. But I do think it's interesting that well before we had BEM in 2010, and we had the false positive paper, and we had the Reproducibility Project, Cumming and other people were already talking about how poor this metric of replication was. Not too surprising, Cumming is going to come out of this. He's the new statistics guy. He's going to come out of this saying, let's not use p-values anymore. But I do think that his point is something that we already know, right? We know that p-values have a distribution. They have their own sampling variability. And he points out that that distribution or that variability can be quite wide. So there's a couple ways to look at that. If you're not already familiar with the many wonderful resources that are psychologists, this is just one looking at the p-value distributions. So what I did here is I set it up for what is supposed to be the average effect in psychology. So that was found to be an R of 0.21, which translates into a D of 0.43. That's almost certainly an overestimate. And then an average power. And so most of the power estimates are coming in that we're getting about 50% power in general. So usually in replication, we're obviously aiming higher for that. But I just wanted to show you here that when you have only 50% power, half of your p-values are going to be above 0.05 and half are going to be below 0.05. So it still is consistent to find a p-value that's larger than 0.05. You can still find that even when you have a true effect. And that d at 0.43, I mean, that's a medium effect. Another way to look at this is, again, another great resource, and there's even an R package now for the new statistics. So this is just the web app on it. And again, I set it up for the same thing. So you do that average effect size, average power. And you can see here, that column there with the little squares, and there's a 0.023, 0.00, 0.001. This is a simulation, a sampling from that distribution, from that effect. And these are the p-values, and they range from 0.001 to 0.982. Now, if I found a significance level of 0.982, I would be there, there's nothing to see here. This is obviously, nothing to look at with it. But that is possible even when our true D value is a medium effect, is we can get a p-value that high, that wide of a range of p-values. So Cubby also in his paper shows this. Those are all simulations, assuming I know what the power is, I know what the exact effect is. But what if you only know the p-value from the original study? And again, you can see here, so that's what the different lines are. That's what p-OBT is, p obtained. So those are different lines for that. And then along the x-axis is what the p-value would be one-tailed in the replication study. And again, you can see we get a wide range of values, and not all of them, most of them, but not all of them are falling below 0.05 with that. So again, the problem with the p-value as a measure of success is that it leads to the mistake of accepting the null hypothesis rather than just failing to reject it, that there is this distribution. But the other one I wanted to bring in is, again, maybe this is my age showing, but there was a period of time right when all the crisis stuff started to gain attention, saying that it was a bad thing if you found significant effects too often. So Francis wrote a large number of papers on what he called the test of excessive significance. Shimak had what's sometimes called the test of insufficient variance, or the incredibility index. And now he's moved on to the replicability index. But the idea here was that we should be highly suspicious if you get a significant effect multiple times. So often this was done when you found when someone reported significant effects within a given paper. So this is from one of Francis's, looking at a study by Balcetis and Dunning. And so what he does is he takes the power for each of those effects, and he calculated out just by multiplying. So that power would be the likelihood of detecting a significant effect if indeed one exists. You can see here across those 5 studies, you get a 0.076. He sets the cutoff at 0.1. Another way, though, to look at this, and this is what the conclusion is from Francis, it's just not believable that you could have so many rejections in the null hypothesis. So another way to look at this is, what's the likelihood that we would have 2 p-values that are less than 0.05? So if the original study only had 50% power, which is highly likely if that's what our average power is, even if you power your replication to 0.9, the likelihood of finding 2 significant values that are less than 0.05 is only 45%. So I do remember when this came out and there was a lot of calls. I looked last night and I couldn't find it. I seem to remember even people like Samin Vazir saying, like, we need to be less strict, that there is going to be messiness, that there's going to be some p-values that are not significant and some that are. So I find it interesting that we are being so strict now that the replication must necessarily have a p-value less than 0.05, when there's these other indications that maybe that is problematic when we see too many p-values being significant. The other one, this is my favorite quote of all time. If you take a class with me, you're going to hear me say this ad nauseum. Gelman and Stern, I think, is also right up there with the false positive paper in terms of papers everybody should read. But really, it's just, this is the title of the paper, and this is the take-home point. The difference between significant and non-significant may itself not be statistically significant. So the point there is that just because one was significant and the other was not, doesn't mean they're significantly different from each other. And that's what we would want to know. It seems, again, I'll talk a little bit about goals for replication, but that's usually one of our goals is to say, did we get something different? Did we find the same thing again, or did we find something different? So the example I'm actually taking from Maxwell and colleagues' paper, they looked at the Wertman replication of Barge and Shalev. So the replication study had a D of 0.02. The original study had a D of 0.61. So that looks really bad. But the p-value for the differences between the effect sizes was not significant. So again, one potential explanation is this is just part of that sampling variability. So that's the replication p-value. That's probably the one you know. That's the easiest one to use by far. And so certainly those papers that I've been referring to there, Cumming and Maxwell. So one of the things that they then advocate for is let's look instead at effect sizes. So one way to do that is, does the original effect size fall within the replication effect size, either confidence interval or prediction interval? I'm going to focus first on the confidence interval because, again, I'm coming at this from more of a frequentist perspective. I'm not a Bayesian. And so that's probably the one that most people might be familiar with. I actually have seen it done the other way. So does the replication effect size point estimate fall within the original study's confidence interval? But the way Cumming and others laid this out is in terms of, does the original effect size fall within the replication confidence interval? And then part of that as well, and this is again coming from Gelman, is he says, let's not be so concerned about significant or non-significant. Let's be concerned about a type M or type S error. So is it a higher or lower magnitude? And is it the same or the opposite sign? So that's another thing that people look at for the consistency of effect sizes. So what Eddie and Lavelle and his colleagues did is they proposed a way to kind of bring those things together. And so looking at first, whether or not a signal was detected. And so that's just our basic p-value one. So does a 95% confidence interval contain 0? If it doesn't, there's signal. If it does, there's no signal. And then a way to kind of categorize the consistency of the effect sizes. So consistent, the replication confidence interval contains the original effect size point estimate. Inconsistent, it does not. And then we can further categorize inconsistence in terms of larger. So the replication effect size is greater, but in the same direction as the original effect size. Smaller, the replication effect size is in the same direction, but smaller than the original, and then opposite. And many people obviously point to opposite being obviously the most troubling. So that if we find things are in the opposite, that type S error, that should really give us some pause. They also propose using a relative precision of the effect size confidence intervals, so the width of the confidence intervals. To me, that's engaging in the precision fallacy. So I don't advocate using that one. I think that is not terribly informative. The other thing to look at, though, is even though it falls under inconsistent, the larger and smaller inconsistent really are in many ways consistent, right? They're in the same direction. It's just the confidence interval doesn't contain the original point size effect. So I'm just going to again go back to that study from my lab with Thomas. And so you can see, let's look at that first one, self-centrality. So there's no signal here because the replication, the red line, crosses 0. And the point estimate, the blue diamond, from the original study doesn't fall within our confidence interval, so it's inconsistent, and our point estimate is smaller. So this would be no signal inconsistent. If we look at this one, again, no signal because our confidence interval contains 0, but this is consistent because the replication, the original point estimate, that blue diamond, falls within our confidence interval. So this in a way would be a successful replication, would be a conclusion. And then if we look at the ones down below, so this is actually, these are both, remember, signal, they were both p less than 0.05, the confidence intervals don't contain 0. But this one would be considered inconsistent, but I wouldn't hold this against the original study because we found a larger effect. So this would be signal inconsistent, but larger. And this is also signal inconsistent, but larger. We found larger effects in our sample than in the original sample for both of those. So that would be a way to kind of apply that rather than just does it fall in the confidence interval or not, kind of giving some qualitative conclusions as well about the nature of that relationship. So another example kind of making this point is from, again, Maxwell. So this is directly out of the paper. If you are taking notes, you don't need to you can go right to the paper for it. So they say, suppose the replication study found, T 1.5, p-value 0.14, and a D of 0.23. That's the effect size. And the confidence interval for that effect size contains 0. So 0 is a plausible value. And I do like to emphasize this to my students. Just because 0 falls within your confidence interval doesn't mean that it's the true value. Doesn't mean that it's the only value. That's the way we often seem to interpret it, is that if 0 is in our confidence interval, well, that's it. It's a null effect. But I think to keep in mind is that 0 is just one of many possible values. That confidence interval also contains 0.5. 0.5 is a medium effect. So we have as much evidence that it's a null effect as we do that it's a medium effect. So why do we conclude that it necessarily has to be a null effect and can't possibly be evidence of a medium effect when we have equal evidence for that? And then I think another thing that Maxwell and colleagues also make is that it's probably going to take more than one study. I'm really talking here about situations. I'm not talking about many lab in this kind of example. I'm talking about, like, what am I doing in my lab? When we do a replication study, how are we making these decisions? And one additional study isn't really going to be enough for us to fully conclude that what's true out there is a null effect. You likely need what's been done with those many lab, kind of replications over time, even. So rarely will a single study be sufficient. And so one of the conclusions from this, and this would also be, again, consistent with Cumming, because this is one of his new statistics, which, of course, as you know, are all old statistics, is maybe we should do a meta-analysis instead. So let's look at that. So the other criteria is the meta-analytic effect size significantly different from 0. So again, I'm going to take this straight out of a paper. This example is from Fabregat and Wagner. So suppose the original paper had 3 studies with 40 participants, and we find effect sizes of 0.67, 0.57, 0.77, so all medium to large, and p-values. So 2 of them are significant, 1 is not. And each study only had 54% power, and we only found here that 2 were significant. Now suppose that the replication studies also have an N of 40. Very often they are larger, but that's not always the case. Even within those reproducibility project and many lab projects, they're not always larger. And suppose that then these 3 replication studies, it's 0.32, 0.24, and 0.4, and none of the p-values are significant. So that looks bad, right? That looks like we didn't replicate. So overall, even if you look across both sets of 6 studies, there are more that have p-values that are non-significant than have p-values that are significant. So our conclusion likely would be for this topic is that we have failed to replicate, that perhaps there is nothing really there worth looking at. But if you look at it meta-analytically, you get very different conclusions. So if you only meta-analyze the first 3 studies, you get that the effect size, the meta-analytic effect size, is significantly different from 0. Now, what happens if you add the 3 replication studies to the first 3? You still get the same conclusion. In fact, the z-value has gotten higher for that. So you might even say you are even more confident that 0 is not the effect. So, so that's just demonstrating, again, how heterogeneous our conclusions can be depending on which metric we use. So the next one I'm going to talk about is Simonson's small telescopes. And I will say that we use this in practice for deciding how many participants to run for a replication. That little rule of thumb of 2.5 times the original study is very useful, very easy to implement, especially if you're using, the graph I was showing you is actually using multi-level modeling. That's we don't have a lot of good power programs for multi-level modeling yet, although many have been developed, are getting better about that, or even agreement on what that effect size should be. So that 2.5 comes in handy. I will say though, in practice, and again, I haven't read every replication study out there, that I don't see people applying this very much, but let's go over what it is, because I'm saying on one hand, useful, on the other hand, not many people are applying it. So his idea is that is the effect size in the replication close enough to 0 that the original study would have been unable to meaningfully study an effect size that small. So this is the idea that he uses the analogy that if you can see a planet with a small telescope, you should be able to see the same planet with a larger telescope. So that's sort of the contrast between the original study being the small telescope and our replication being the larger telescope. So it's a way to kind of combine null hypothesis significance testing with effect size. And so what he defines as a small effect is one with 33% power to be detected in the original. So basically 33% of the original study effect size. And so if a replication with effect size that's significantly smaller than that 33% would be inconsistent with the idea that the study that was found in the original study was large enough to be detected with that original sample size. So the example that he uses is, suppose there's an original study, 2 conditions, 20% is our typical t-test setup. What effect size would give this study 33% power? He calculates out, so that's a D of 0.5. Then you use the replication study to test that the null hypothesis either equals 0.5 versus the alternative that it's smaller than 0.5. And if you reject the null hypothesis, the original telescope was too small. So it was too small to have detected sort of reliably that effect. So I think graphically it might be a little bit easier to see this. So these, again, are real data. The original study is by Zong and Lillenquist. And so that's the first line, the first vertical line there. The second one is a replication, so 5 years later. And you can see here that the confidence interval, the replication contains 0, so it's not significant. But it also does contain the D of 33%. So that's that small telescope D. And that's what the dotted horizontal line is. So this would be considered a replication success. Then we look at the other one. So this is a confidence interval, the replication contains 0, but doesn't contain that D of 33%. So we reject the null hypothesis. And here this would be considered a replication failure. So as I said, I haven't really been seeing people use this. And I said I've been going to a lot of these talks. I went to a talk by his colleagues, the other 2 people that form Data Colada, and they've been doing something they call data replicata, where they've been replicating studies from the Journal of Consumer Research. So what did they use? You think if somebody's going to use this, it would be your colleagues that you share a group with. They use p-values. And they only use p-values. And someone said, what about confidence intervals? They said, oh, sure, we could do that. They didn't seem to have any indication that there were other ways to look at this. They looked just purely at p-values with it. So that brings us then to another thing that has been proposed, and that is equivalence tests. And so this is looking at equivalence to 0. I would propose, and I'm surprised that we don't have people advocating for this, is I would be interested in looking at equivalence to the original study, but this is still applying just your basic equivalence test. So is the replication significantly equivalent to 0 or not, to a null effect? So if it's entirely within equivalence range, then we'd say replication failure. If it's entirely outside the equivalence range, we'd say replication success. If it overlaps with the equivalence range, then it's inconclusive. And so again, Wortman used Maxwell used the Wortman et al. Replication and Barge and Shalev. Again, the original study had a D of 0.61, the replication study of D of 0.02. The 90% confidence interval for the replication does contain 0. But it supports then a null effect only if you conclude, so only if you set your equivalence boundary to be a D of 0.22. Now again, a D of 0.22, at least according to Corwin's guidelines, and that's a separate discussion, is a small effect, but it's definitely not a null effect. with it. So again, we're concluding that we have a null effect here, but it may not be statistically equivalent to that. Of course, there are some problems with this. So Simonson in his small telescopes paper was pointing out it's difficult to figure out what your smallest effect size of interest was. There was a recent talk by Envari on that. So it is something, you know, a lot of our theories just say something should be bigger, but they don't say how much bigger than the other group or things like that. So it can be hard to decide what that is. And it is true that you need a larger sample size to detect equivalence. In fact, Maxwell says, stop powering your replication to detect significant difference. Instead, power your replication to detect significant equivalence. But when we look at these numbers, if these are what our smallest effect size of interest are going to be, our SSOIs, so 0.05 and 0.1 as a D around 0. I mean, we're needing, this is thousands per group that we would need. So even at 50% power, we would still need 1,000 participants in each of our two groups. That's over 2,000 participants, which may be beyond the resources that most of us have. Again, you could set that SSOI larger. You could decide that indeed, I don't think a small effect is kind of worthwhile. I think a small effect is like a null effect. And so then the 0.2 would make sense. And so then the last one are some Bayesian methods. Again, like I said, I'm not a Bayesian. Everything I know about Bayesian methods, I know from Danielle Navarro's chapter in Learning Statistics with R. It's always on my list of things to learn, but let's go through them. So there is something, a Bayesian method that's like an equivalence test that I just covered. So there's a region of practical equivalence, or ROPE. Instead, it uses a credible rather than a confidence interval. And a prior distribution comes from for the effect size. One of the problems, at least that Maxwell points out, I can't independently verify this, is it does require access to the raw data, which you may or may not be able to have. In your lab, I would guess yes. Outside your lab, probably not. There is the Bayes factor, so you compare how probable is the null hypothesis versus the alternative, given the replication data. And then we can look at these various levels of evidence. So it could strongly support the alternative, or it could strongly support the null. So let's just put some of these into practice then. And so I'm just going to use the Reproducibility Project because it's one that's most have been written about, and they did look at various ways. So of the 100 studies, 97 original studies, the effect that they were looking to replicate did find that the original study found a significant effect. So this is the one I'm guessing you know. When we talk about what's the replication rate in psychology, I'm guessing this is 36% is the one that you say. And so that's using purely the p-value. So 35 of those 97 studies that originally found a significant effect found a significant effect again. So that's our 36%. But you can see we get a wide range of the distribution. So the one on the left is the p-values for the original study. The one on the right is the p-values for the replication studies. So they also looked at effect size within their paper, and overall that had a 47.4% success rate. So overlap between the point estimate of the original study in the confidence interval of the replication. But again, you can see we get a lot of variability in that as well. So one of the things I did, so at RIOT Science, remember LaBelle and colleagues are the one that had the categorizations of how to look at those confidence interval overlap. So they have, again, a searchable table of 1,127 replications of 168 effects. So these are not completely independent. So I wouldn't want to make too much of that because they're often looking at the same studies that are being replicated. But you can just type in RPP there and look at just the 100 studies that were replicated in the Reproducibility Project. And so when I did that, I found that in terms of no signal, they have one where they didn't specify any consistency. They had 22 that were consistent. They had 40 that were inconsistent, and 16 of those were in the opposite direction. In terms of the signal, they had 31 that were consistent, 4 that were larger, 2 that were smaller. So overall, we can either calculate that we found 59% consistency, in the reproducibility project, or if you only take out the ones that were opposite, we're getting about 84% consistency. The other thing they did is they did the meta-analytic effect size. So they combined the original and the replication. And when you do that, 51 of the 75 found a meta-analytic effect size significantly different from 0. So that's a 68% success. Another way to look at that is the correlation. So we're looking at here the similarity between the original and the replication. You have a correlation of 0.51, which again is significant. And that's what that looks like. So it looks pretty good. And then there's a Bayesian reanalysis. And this, in fact, looks the best, although there is a big caveat to this. So overall, they found 75% of the replication found similar levels of evidence. And I kind of have that emphasized in because they went through and calculated Bayes factors for all the original studies and concluded that a lot of the original studies did not have substantial evidence. So we're saying here there's similarity between the original and the replication, but I'm not necessarily saying that there is an effect or a substantial effect or evidence of a substantial effect based on that. And so this is what theirs look like. So just some additional information, 64%, neither the original nor the replication yielded strong evidence. Only 11% did both yield strong evidence, so that doesn't look good. 15% of the original study supported the alternative, but the replication did not. 10% the replication supported the alternative, but the original did not. So that's kind of qualifying some of that evidence. And so this is what we get if I look across those various things, and you can see that there's something here probably to make everybody happy. The people who think there's a replication crisis and the people who don't. So if you are think everything is wrong, you have your 36%. If you're holding on to some hope, you have your 68%, maybe the 75%, but again, that 75% is a bit misleading since so many studies, they concluded just none of the studies were finding evidence for it. So there seems to be something for everyone. And that's always problematic, right? That's our garden of forking paths, or I don't know, like success replication hacking, which one you want to choose for the conclusion you want to make with it. And that's what I find to be a bit problematic is we don't have good agreement on which of these we should look at. So that leaves it open to people using whichever one yields the conclusion that they want to have in the end with it. And so that's something I would advocate. I hope that our field starts moving forward into different ways of deciding that. And so the other thing I did is I looked at all of RIOT Science just across those 1,200, easy way to do it. So 60% had no signal, the replications. Only 33% did find a significant effect again. But if we look at overall consistency, we're about 42%. Again, it's not great, not saying that's not much better than at 36%, but it is a different way of looking at it. And again, these are replications largely going at similar effects. So it only was 168 effects across the 1,200 studies. There have, though, more recently been some simulation studies to try to put, to test these various methods. So just published this year, Shower and Hedges, found that both the p-value and that confidence interval overlap, so does the effect size of the original fall within the confidence interval of the replication, are more likely to lead to false conclusions of non-replication. This will be a false negative, according to that criteria. The prediction interval does very well, but it has lower power when there's only 2 studies. And I said, a lot of times that's what we're doing, right? I just have that original study by Gebauer and then the one that Thomas and I did with some of our students. The meta-analysis seems to do a better job of estimating that actual effect, but it's a little bit harder to conclude whether the replication was a success or failure based on that. So again, maybe you do the meta-analysis if you're just trying to find out closer to what some evidence for what the true effect is. And it's also, like they point out, can be problematic when you have 2 effect sizes that are similar in magnitude but different signs. So they kind of cancel each other out. So your analytic effect size will be 0, but clearly something different is going on there. When the original study was positive and the replication is negative, it's clear that the effect size is not 0, but what's going on there with it. More recently, there's a preprint looked at the significance criteria as well as different methods. And then they also varied the rate of publication bias in their simulation. And so their conclusions are, in general, the Bayesian methods do better than the frequentist methods, except for the replication Bayes factor. Overall, the Bayes factor and this new measure, the skeptical p-value, which is also sort of a Bayesian metric, performed the best. Meta-analysis, both the frequentist and the Bayesian did better than any of the single study metrics, except when you had high publication bias. So if the publication bias was at 100%, they both yielded pretty substantial false positive rates of 41% and 31%. The small telescopes had the highest false positive rate, so seemed to be too liberal in concluding you had replication success. It ranged anywhere from 24 to 52%, depending on the publication bias. 52% was at 100% publication bias. So maybe it's a good thing that people aren't applying the small telescopes as a criteria. As I said, I can't really find anybody doing that much. So which one should you use? So Anderson and Maxwell had proposed it really depends on your goal. And they have this table. So if you just want to say, did you have a replication effect or not, then the p-value. If you want to infer that you had a null replication effect, then you really should do an equivalence test. If you want to precisely estimate the replication effect, then you want to do one of the confidence intervals. If you want to combine the two, so you want to get a good estimate of that effect of the study, then like a meta-analysis. If you want to assess whether replication is inconsistent, then again, the confidence interval. If you want to assess if it's clearly consistent, then again, either equivalence test or the confidence interval for that. So what are my take-home points? The point I want to make is not the p-value. If you need an EC metric, you really can do basically the same thing with the confidence interval, and then qualify that confidence interval information by using perhaps Lebel's categories I've been finding fairly useful. The other one to do is a meta-analysis, or if possible, if you can get access to the data, so if you're replicating things within your own lab, do an integrated data analysis. Combine, you put that larger N together, use study as a factor, and see if you get a significant difference that way. And then if you're comfortable, the Bayes factor, there's no doubt that that's performing well and giving us some additional information with it. So that's all I had, and I'm happy to take questions, Thomas, if you had any.
Hi there, yeah. Actually, I thought maybe I'd just give it a minute just to give people a chance to kind of digest and perhaps put a question up. But while we're potentially waiting, I'll start you off with one question, perhaps. Had a few notes here. I'm just trying to decide what the best question is. So, yeah, obviously with us, we had this opportunity with when we were replicating some original authors who were extremely open and transparent at every stage of things, where they actually did, share the data with us so that we could run an integrated data analysis, for example. I was just kind of thinking, do you think there's other advantages to that, even above determining the most effective estimate of the effect size? And just to give one example of that, you imagine there might be things like gender differences between the two samples. And it could be the case that there's not a significant moderation effect of the effect size in either study alone. But when you pool it together, all of a sudden you find that perhaps gender does make a difference. And in fact, one of the samples showing an effect and the other not showing the effect might ultimately have been driven by that. And one can imagine other things along those lines. I guess I'm just curious, do you think there's other bonuses to pulling all of the data together and using this kind of IDA approach?
Yeah, I think most definitely that's true. Like even my student Erica just defended on Wednesday, and her study was all based on replication, and the prior data collection from our school, our lab, had about 20% men. Her study had about 4 to 6% men. And so you can't really evaluate a gender effect in her study, but she pulled them together, right, to see if there was anything there potentially that maybe the reason she wasn't replicating the earlier time period was because of that sample difference, rather than something maybe historical that had changed over time. So I definitely think that's true. It would certainly make it easier to investigate those moderators directly. So there is a way to do that within meta-analysis. But even like the example that I was pulling from Fabrigar and Wagner, they make the point like there wasn't a heterogeneous effect size there. So there wouldn't really have been a reason to look at moderation. But we know that interaction effects from the data colada guys themselves there, even Simonson shows, that we often need 4 to 8 times as many people to find moderation. And so certainly that would be a benefit of it as well. That the law of large numbers, we're going to get a better estimate of the effect, but we can also maybe do some of these more complicated designs as well.
Okay, yeah, fantastic. I don't see anything in the Q&A quite yet, but I did have another one I wanted to ask. So I was thinking about the equivalence testing stuff that you were discussing, which I always find really interesting. And it seems like one of the potential challenges with that is determining what is the smallest effect size of interest that you'd be willing to consider meaningful. And the first thing my mind went to was kind of the sort of Alice Eagley stuff with gender differences, and if you can show across a meta-analysis that there is a D.1, man-woman difference on some trait, is that meaningful? But it's subjective, because maybe to me a 0.2 is the cutoff for meaningful, but for someone else a 0.1 is. I thought, maybe conceivably one way to partly get around it is almost polling people who are involved in a research area, maybe people who have frequently published on gender differences, let's say, and asking them, well, given your theoretical background, given your orientation in the field, what do you believe is kind of your cutoff, and then trying to determine from a body of scientists kind of what that. I'm not sure whether anyone's ever kind of taken that approach before, if you see any value in it.
It's been recommended. So when I teach equivalence testing, that's one of the things I cover, is how to choose your sesoi. And so like Cumming and others have said, like, what is a clinically meaningful difference? So he actually polled, people who did work with people with dementia. So what would be a clinically meaningful difference for that group? Or you could think of like, I use the Beck Depression Inventory a lot in my research. So there are sort of values or cutoffs that correspond to like severe depression versus not. And so I could say like, well, what would be sort of a meaningful change? Like changing from a severe depression group to maybe non-depression, would be like 10 points difference or more. But that might, again, I think you're right, going to, I think it's going to be hard to draw it out of our theories, because I said a lot of times our theories are just, it's going to be greater than this group, than that group, and we never say how much. We're not physicists. But yeah, that's one way that has been proposed to do it. And then sort of like what, I think that it does take us to kind of step back and say, what do we think is a meaningful difference? So sometimes when I see presentations in social psych, my field, there's a lot being made out of a 0.5 difference on a 1 to 7 scale. And I'm like, would I see that? Would I notice that? So it's significant and probably has a medium effect size, but would I meaningfully see that difference in 2 people? So someone who liked the attitude object 0.5 versus 5.5. And so I do think we sometimes need to step back and maybe even get away from, what's a small, medium, and large effect size according to Cohen, and be like, what would be a visible effect size? And so I know there are some people, I think Hart Blanton and maybe Jesse Sun have tried to do that, saying like, if you fall on this scale, like, an extroversion, how many more parties do you go to on it? Kind of taking that kind of more practical or behavioral approach to those scale items with it. And then maybe from that research, you could develop what would be sort of, just too small to be meaningful difference. I think Lackins has written a lot on this. Actually, my very, very first academic conference presentation was on equivalence testing, so it's near and dear to my heart. Way back in the 1990s, early 90s, talks about that. Like, you just have to say like, what, like if you're in an applied field, if I'm going to throw money at this, how much difference do I need my intervention to have? Or, what would be meaningful for me to say that this is a, you know, an important difference, an important change, or whatever it is. But yeah, I don't think we again have, and I don't know that we should expect that there's just one way to do it. But I do think it's something it's something you'll definitely have to justify doing, why you chose what you did.
Yeah, actually, it's funny. Some of your discussion reminded me, I think John's done some stuff looking at whether the public is sort of impressed by the effect sizes that psychologists tend to put out, for example. And you imagine there could be a difference there as well, that specialists in the area sort of have one cutoff, and then the general public, if you can find a way to translate that meaningfully to them, are they impressed again by that effect size, or what's their cutoff? Okay, so there is one question as well I wanted to take from the Q&A. This is from Jenny Murphy. So she says, great talk. My research group are heading the Sports Science Replication Center currently, and interpreting replications is something we have thought a lot about. What are your thoughts on combining methods for determining if replications are successful or failures? Should a replication study hit all criteria to determine if successful, or would you advocate using one method only?
I do, like a lot of these papers, certainly advocate we need to do more than one. Probably one isn't sufficient. I think only thing I'm coming strongly down on is not the p-value. I just find that very dissatisfactory. It's performance, what we know about it, and it's certainly the easiest one to use. But yeah, I do think that multiple probably is better. I mean, to the Reproducibility Project's credit, they didn't just use the p-value. Unfortunately, that's what gets drawn out of all the press about it. And that's what we seem to remember, because that's the first one they covered. And that's the most shocking one. And maybe we needed that. We needed to be shocked with it. But yeah, I certainly would. And I like this idea of kind of frequentist Bayesian. I just wish I was a little more comfortable with the Bayesian. And we actually tried, I don't know if you remember this, Thomas, I was trying to do the replication base factor. Maybe it's good that it didn't work out since it doesn't seem to perform that well, but I couldn't get it not to be circular. And I went to Alex Etz and he just said, read the paper, and that didn't help me. Anyway, but I saw in the RIOT's talk that Wagemakers is going to give a Bayesian talk, so maybe you all will become more familiar with those techniques. But I always like when those two camps, when you can find agreement between those two camps, I think that's compelling. So maybe using some kind of confidence interval, meta-analytic effect size, and then the base factor as well. So we can kind of get converging evidence from very different approaches to it. That I find that compelling as well.
That's it. Yeah, I really like that answer. And I guess one sort of follow-up thought, I think my impression, at least with meta-analysis, is that over time it's become the case that more and more different approaches to, for example, correcting for publication bias have become common. And at this point, it's sort of considered almost a courtesy to include a whole bunch of them. If for no other reason, then, once people are broadly familiar with the different approaches, it doesn't add a lot of space to add the additional detail, but it can be useful to at least somebody out there who comes at it from a specific statistical orientation, maybe.
Right, because we don't have a good consensus on that either, right? We don't have a good consensus on how to correct for publication bias. None of them seem to work well all the time. And I think that's the case here as well. None of these seem to work well all the time.
So that was the only other question we had from the Q&A. I don't know if John, there was one other one actually I was going to ask about. So someone was asking, Jill, would you be okay with sharing your slides? Oh, I think John already answered that actually. Yeah, so if you're comfortable with that, then we can go ahead with that.
Is my mic working now? Can you hear me?
Yeah.
Yeah.
Okay. I don't know what happened earlier. Because I do have a question actually really quickly.
Sure.
You talk a lot about meta-analysis, and I remember this paper from Vosgaro, Simonson, 99% impossible, and they pointed out lots of issues with particularly on internal meta-analyses, but they say that these issues apply also to external meta-analyses as well. Mainly that they severely inflate the false positive rates very easily. So what would the implications for that what would the implications be for this in terms of replication? So
yeah, I mean, there is an issue of selection bias, especially when you're looking at cross. I mean, there is though a whole paper on using what's called a cumulative meta-analysis for replication. So kind of adding, as we get these additional studies, adding them up with it. But yeah, you're often missing, well, I'll take the bigger picture one where you're doing the meta-analysis across. And so it's really hard to get those published studies that aren't published And none of the correction, the publication bias correction things, at least that I've seen so far, all of them have flaws. All of them are going to fail at some point. There's always a new one on the market, and so we'll see how they play out. I guess the idea within a study is, again, maybe it's like within a set of studies, is, again, maybe it's limited because it's not the full sampling range. But I think, to me, anything that kind of brings things together at least should give us a better estimate based on that limitation. So there, there's a lot of people talking about, like having that paragraph in your study. So what does this generalize to? Maybe that's what you have to do here, is I can only really, for my sample at this school, here's my best estimate of what it is. And maybe we should be more cautious about extending beyond that. So yeah, there's definitely, and we've seen that, right? When we compare what's happened with meta-analyses of certain effects versus these multiple lab replications of certain effects. So ego depletion looked really good in the meta-analysis, doesn't look so good with Bose and colleagues, multi-lab, multi-study kind of replication for it. So we know that they're not perfect. We know they're likely missing some things. So I think that's true as well. But we only have so much evidence for it, and it is a way to kind of combine that evidence together for what we do have. But no, it can't be the be all end all with it. And I certainly recognize that there are those limitations to it. And at least when we look at the published literature versus what's done on those many lab kind of things, they aren't matching.
Cool, thanks.
So I believe that brings us to the hour mark.
Okay.
Jill, I'm not sure if you had any kind of closing comments you wanted to make, or if anyone else had any kind of last second questions here, happy to catch those. But if not, thank you so much, Jill. It's been great to hear your thoughts about all this stuff. I know I've learned a lot. I'm sure everyone here has learned a lot.
As I said at the beginning, I had kind of a selfish thing for wanting to do this topic to make me go and finally all the stuff that I've been gathering to go through it. So it's been very useful to me. And so I thank you for the opportunity.
All right. Take care.
All right.
Thanks.
Bye.
Thanks, everybody.
Bye.
I'm actually going to stay on just for a second, mostly because I wanted to just make sure I'm closing this correctly so I don't mess up a recording or something. This is my first time doing one of these things. I think, Jill, you'd be okay to head out.
Okay.
I don't mean to don't hold you up, but I meant more for John and Tweedy if she's still there.
Okay.
Thank you. Thanks, Jill.